Okay, hello and welcome back to Astronomy at Home, brought to you by the DiRAC Institute and Astronomy on Tap Seattle. We're so glad that you could join us again for another night of fantastic science. We have a great talk coming up for you, but just before we do that, some of the usual reminders. We'll have our Q&A session with the speaker immediately following the talk, so feel free to add questions along the way, either in the Zoom chat if you're following along on Zoom, or the YouTube chat if you're following there. Then at 8 p.m. after a short break, we'll have our Instagram live interview with the speaker on AOT Seattle's Instagram. I'll post the handle in the chat if you'd like to join us for that. And besides that, let's get started. So our speaker tonight is an NSF Postdoctoral Fellow in the DiRAC Institute and Astronomy Department of the University of Washington. Please give a warm, if silent, welcome to Dr. Keaton Bell.
I'm muted. Hey there. It's nice to be with you. I'm really excited to share with you about a technique that I use to sound the interiors of stars. That is, I'm able to use a telescope to measure the vibrations that are taking place within distant stars and use them to decipher the properties of their deep interiors. These are some of the most difficult regions of space to access, as they're buried deep below the visible outer surfaces of stars. Yet we're able to probe these depths by analyzing precise video recordings of vibrating stars. But I want to start somewhere else today, somewhere in the world of espionage. This article from Wired really caught my eye a couple of months ago. It described a technique developed by an Israeli research team for eavesdropping on conversations by observing the brightness of a distant light bulb with a telescope. And I thought that that sounded a lot like what I do for work, using telescopes to observe the brightness of distant stars. So to help bring you along on this journey into my world of trying to understand how stars work, I thought I would start with this more relatable example from your world of trying to keep your secrets safe from nosy eavesdroppers. So this is the setup for the spy technique. Somewhere there's a distant victim's room where a secret conversation is taking place. And there's also a hanging light bulb in this room that must be visible through a window. So with this victim set up, with the window open, there's a eavesdropper then that sets up somewhere else with a line of sight view of this light bulb. And they point a telescope at the victim's room window. The spy's situation is similar to that of an astronomer who wants to understand how objects in space work and can't travel to these objects to make direct measurements. Perhaps it's too dangerous for the spy to infiltrate this room and say, plant a bug. They can't directly manipulate or hear the conversation, but they've got to infer what's going on from a distance, only based on the properties of light that they record, the light that has traveled across the intervening space to reach their telescope. So inside the room, the medium for the conversation is sound waves, whether there's some in-person conversation or some phone conversation you can hear, one side of. These sound waves are vibrations in air pressure. And these air pressure vibrations, they vibrate our eardrums to create the perception of sound, but they also bounce off of everything else in the room, including this hanging lamp. And this lamp, because it's just hanging on a simple cord, it's able to freely vibrate on its cord right along with the conversation. As the lamp vibrates, it moves slightly closer to and then slightly further away from this telescope. And as it does, it appears to become a little brighter when it's nearer, a little fainter when it's further away. So the spy measures the brightness of this light bulb, passes through its telescope and onto this detector, and it passes this recording of brightness variations through some algorithm that converts that record of brightness from the light bulb into a real-time conversation that the eavesdropper can then listen to. So this use of a telescope to eavesdrop on a conversation by measuring the minuscule variations in the light bulb's brightness is strikingly similar to how I use telescopes to probe the physical conditions inside of a star by recording its brightness variations. So to prove how well this so-called lamp phone technique works, the researchers, they played a couple of songs. They played Coldplay's Clocks and Let It Be. And they played these songs in the room with the light bulb, and then with their telescope, they were able to record those songs, re-record those songs from a distance. And here's an example of what one of those results sounds like. Clocks, it's a very lo-fi version, very lo-fi clocks, but you can tell what it is definitely. And stars also vary in brightness because of vibrations inside of them. So vibrations that are occurring inside of a star also vibrate the material of the star, just like they vibrate this lamp on a cord, and they act like a dimmer switch on the star's brightness at its surface. So this animation that I've put up now, this shows what the brightness across the surface of a star might look like in response to vibrations that it's experiencing. The bluer colors that you see are brighter, temporarily brighter regions of the star, and the redder colors are fainter regions. And then overall, if you measured the brightness of the total disk of this star over time with the telescope, you would see this record of brightness that's at the bottom of this image. And that's the type of thing that I would measure from my telescope. So one telescope that I use for this sort of work is a 3.5 meter telescope at Apache Point Observatory in New Mexico. And to measure how the brightness of stars vary with time, I record movies of them, which are quite similar to time-lapse images. So here's a sequence of images from my most recent run at Apache Point Observatory. And these images contain a dramatic example of brightness variations from one of these stars. So to orient you with what typical telescope imaging data looks like, we usually get a black and white image, and the stars show up like these white points along a dark black background. Do you notice any of these changing considerably? This one right here, if you watch it, it disappears completely and then comes back. And this is something that can happen if an object like a planet were to pass in front of a very small star and block out most of that star's light. So here's a little simulation of what something like that could look like. Here I show as a planet this black dot that's moving around in an orbit around this very small star that's represented as a blue dot. And as it moves in its orbit, this line on the top is tracing out what the brightness of the star appears to be as we measure it. And when the planet passes in front of this star temporarily, it causes that brightness to really dip down enough so that the star could potentially disappear in our images and then reappear. So this is a common method used to detect planets around other stars. If you want to hear more about how I use this technique to detect planets and discover new planets, there's a recording of my last Astronomy on Tap talk on the AOT Seattle YouTube page that I encourage you to check out. The brightness variations of a vibrating star look somewhat different. They look more like this, where each blue dot in this figure represents how bright a star appeared to be in an individual image that was acquired from the telescope. And so expressed in terms of sound, volume might affect really like how much you hear, but the music that you hear is really in the frequencies that are sounding together. And so we use a mathematical trick to transform our recording of star brightness over time, like you see here, into a new representation that shows what frequencies are ringing out in the star from that overall record of brightness. This is a different way to visualize how the star is varying. Well, the blue curve at top shows the changes over time. And this really summarizes what frequencies are present during this time when we were recording. So every little spike in this image represents a different vibrational tone that is ringing out in this star. And the taller the peak, you see all these different peaks here, the taller the peak, the louder that signal, the louder that tone is in this star. So you can imagine each of these spikes like a finger pressing down along a keyboard. And the height of each peak represents how hard the key is pressed. With these frequencies ringing out together, my job is essentially to measure precisely how a vibrating star is tuned. So the field of astronomy that deals in vibrating stars is called Asteroseismology. Astero being the prefix meaning star, and seismology from the study of the Earth's interior. This animation shows how seismology works. If an earthquake occurs somewhere on the Earth, it'll trigger vibrations that pass into the planet, and different types of waves interact differently with the different layers inside the Earth. And the strength of these vibrations, as measured at different locations on the surface, that's what's shown on top here, it indicate what the interior of the Earth looks like, lets us back out the locations and properties of regions such as the core or the mantle. Seismology of the stars is quite similar. Vibrating stars are essentially experiencing continuous earthquakes that make the star ring out in a sustained way, like a struck bell. Different vibrations travel to different depths, and so they're influenced by the properties of the star at different depths in its interior, and they're particularly sensitive to the locations of different regions, allowing the asteroseismologist to back out the properties of stellar interiors. The physics of stellar interiors are very intense, with pressures and temperatures so extreme that nuclear fusion occurs spontaneously. We can't produce many of these conditions for study inside of a physics lab on Earth. So the vibrating stars provide us with remote cosmic laboratories for probing these forbidden domains of nature where only the tools of asteroseismology can reach. But this is astronomy on tap. Or astronomy in a bottle, perhaps. So to demonstrate how frequencies relate directly to physical structure, I'm going to vibrate my beer. By blowing over the top of this bottle, I can make a sound. I can't really control the pitch. Just does one note. But if I drink a little bit of this and try it again, my beer is getting foamy. I was practicing this with water. Ooh, I might have to go to the water bottle. Let's see. 1 second. Ooh, that's what happens when you don't drink during practice. So here's the water version. This tone tells me something about the shape of this bottle, how much liquid is in it, and apparently also how foamy the beer is. So this is the sound that this beer makes right now. And if I drink a little bit, the tone changes a little bit. Let's try a little more. You probably noticed the tone getting deeper. And deeper still. This is the fundamental law of beer seismology. Less beer equals lower frequency. So if you hear me making this noise from the other room while you're over in the kitchen, I'm trying to signal you that I'm almost out of beer and I would appreciate another. So now that you've seen how to make a bottle vibrate by blowing on it, how do stars vibrate? Actually, most don't vibrate, and only a few types of stars experience these vibrations and can be studied in this way. So most of these stars vibrate due to a similar mechanism to how you swing on a swing set. You might recognize this illustration from the September 1998 issue of the College Mathematics Journal. The essential action that lets you get into a swinging motion is the change in body position at this most extreme point of your swing, where you just eke your body out a little bit further each time. It's hard to find a GIF of people swinging on a swing set without being badly hurt. So ignore the extra water feature in this one, which actually makes it pretty awesome. But I put this up to show, where these people adjust their body positions in case you haven't been on a swing set recently or read this journal recently. Only certain stars have regions in their interiors where if they're pushed outwards, they respond by enabling themselves to be pushed out even further, like a person does when they're swinging. Pulsating stars can be thought to go through a similar cycle where key changes are happening at specific moments, which cause their vibrations to be amplified rather than suppressed. Instead of swinging back and forth, the stars experience a cycle of compression and expansion from these vibrations. And the stars that naturally pulsate are those whose atoms start losing electrons or that change their rate of nuclear burning at very specific times during this cycle. Like how the body position has to change at very specific times to get this motion going or to keep it going. And so I want to end this talk by telling you a bit about the Transiting Exoplanet Survey Satellite, or TESS. They just released this week this incredible mosaic displaying the area of sky that TESS observed over its original 2 years of operations. So TESS has obtained movies of nearly the entire sky, all of this footprint, especially with this spectacular view of the Milky Way contained in it. It obtained movies lasting between 27 days in most areas to up to a year at the polar regions here. And this movie it's the most extensive video footage of its kind. Recorded in these movies are the brightness variations of tens of millions of stars. It's an incredible amount of data that is going to keep astronomers like me busy for decades. And it's where many of today's most exciting astronomical discoveries are coming from. So keep an eye out for plenty of test results in the news. It's now operating in an extended mission where it's obtaining a similar amount of footage, but at an even faster frame rate. So even higher quality movies of the variable sky. And so just as a final thing, I wanted to show some examples of TESS-like data for different types of stars that vary in brightness. These examples come from a work in progress effort to use machine learning to classify the different types of variable stars in TESS so that astronomers can more efficiently sort through this huge amount of data. So the first I'll show is a solar-like oscillator. It's called this because the sun vibrates in this way. The sun actually is a vibrating star, and it's one of the ones that we can study in the most detail because it's so close to us and we can resolve its surface. It's not just a point on the sky. We can probe the inside of the sun. We can also probe the inside of other solar-like oscillators in the same way. These include red giant stars, which are what the sun becomes when it runs out of fuel. When the sun runs out of fuel, it starts to expand into a much larger star. Those stars also experience solar-like oscillations. These things are oscillating because of the chaotic motions of the material at the surface of the star. That's essentially like the material is boiling. This is a video where you can see this boiling-like process. It's called convection, happening on part of the sun's surface. And here's where the stellar vibrations show up in the frequency space. So this is the record of brightness recorded over time. And then this is the frequency representation, like I showed you earlier. These few peaks here are the signal of solar-like oscillations recorded here. And all of these other peaks are created just by the granulation, this convective process that also embeds a signal in the light curve. So typical vibrations of the sun are sort of on the time scale roughly every 5 minutes. And this tells us something about the sun's characteristic size. So kind of like how the tone of my beer bottle tells me about how much air is in it. Stars like red giants, which are expanding and that show this type of oscillation, their characteristic frequencies tell us about how large those stars are. And as you increase in size, as shown in this example of the frequency content, as we look at larger and larger stars, the typical frequencies of the vibrations that we see decrease, the typical time scales increase. And that indicates that, gives us a direct indication of sort of how big these stars are. Now, the size of a star is really important for studies of exoplanets, because many exoplanets that we know about, these are planets that orbit other stars, we can often only figure out their size relative, that's their size as a percentage of their host star's size. So if their host star presents these types of vibrations that we can analyze, then we can understand the size of that star, and then that tells us what the size of these planets are, which is important for us to understand the diversity of planets in our galaxy. So the next type of variable I want to show is a very dramatic one, large brightness variations over very long time scales. This is characteristic of a Cepheid or an RR-Lyra variable. These are very important in astronomy because their pulsation time scales tell us directly how bright they are. And for this reason, these stars are often called standard candles. If we know how much light a star is putting out and we measure how bright it is, then we can determine how far away it is. That's simply because a candle up close looks brighter than a candle far away. So Cepheids and RR-Lyras are important for mapping out distances in the galaxy and the nearby universe. And historically, they've been responsible for providing the crucial evidence that other galaxies actually exist outside of our own galaxy. And then finally, I wanted to show an example of test-like data for a rich pulsator that presents many simultaneous variations, each indicated by a peak in this frequency plot. You can see each of these variations passes through and probes a slightly different region inside the star. And these can all be compared then, the frequencies that we detect can be compared to computer simulations of vibrating stars with different internal structures to determine with some precision what the actual structure of the star we're observing must be like to produce exactly these tones. So I hope you've enjoyed this quick rundown of how stellar vibrations reveal the internal structures of stars, and I welcome any questions. Thank you.
I'm gonna clap for everyone that we can't hear clapping, but I'm sure that they are. That was an awesome talk. Thank you so much, Keaton. We can get right to questions, and we have one from Matthew Karasu. Is there a correlation between the amplitude of the star's amplitude sound and the number of gravitational masses nearby?
So if you asked me that a year ago, maybe, I might have said, no, I don't think so. I don't think there really would be. But actually, one of the most interesting results to me that has come out of tests and the test data was a result led by, the team was led by Gerald Handler, and they found a pulsating star in a binary system. This orbits another star. And that other star was close enough to have a real strong gravitational interaction on that other star. It actually distorts the other star slightly. And they found that that star pulsated only on one side. So the side away from the star pulsated, and the side near the other star didn't, because of the difference in gravitational strength across that star, which I thought was an incredible result. I think you have to be that close, like a very, the gravity has to be so strong that you're orbiting each other basically. But yeah, I think that's an example of how nearby, sources of gravity can affect the amplitude, certainly, of pulsations, and even the difference in amplitude from one side of a star to the other, which is super cool, I think.
That's amazing. I have a question from YouTube, but I just wanted to comment that's super cool. I have not seen that paper, and I love it so much. So it's a question from YouTube, from Courtney Klein. She asks, would having a spatial resolution of the star, like the colorful video you showed at the beginning, give us more information about the star's interior, or is identifying the frequencies present all we need?
Oh, yes. It is my dream to see the resolved, detailed surface of another star. I would do anything for that. So the example that we have is the sun. The sun is the star that's right near us, and we can see exactly what's happening on the surface. And I don't have graphics at my fingertips for this, but you could kind of see from this image that I'm showing right now. You can see my final slide. There's an example. This animation sort of shows what different waves passing through the star might look like. And this one that passes directly through the center, this sort of represents a variation of the whole star changing all in brightness together. But so this one's like that last one you see where there's this very small frequency change. This causes brightness variations that are very small on the surface of the star. I guess I could show this figure here, way back, this one, that shows the brightness variations on the surface of the star. We inferred what this would look like. My previous PhD advisor, Mike Montgomery, made this graphic. We measured the brightness variations of a star, and he was able to model what that would look like on the surface. But these variations, this lava lamp that you're looking at, these are large variations that cover most of the star's surface. There are vibrations in stars that can cause a very fine detail on the surface, very small details on the surface. But we can't really observe that for other stars than the sun, because they cancel each other out. When they vibrate, there's a little region that gets hotter, and there's always a little region next to it that gets cooler. That is, there's a region that gets brighter, and there's another little region next to it that gets darker. And so they cancel each other out, and we can't see those vibrations for other types of stars. We do see them on the sun because we can resolve the whole disk of the sun, just like if this, if this was a complete record of what the vibrations on the surface looked like, it would be in much higher resolution. So yes, if we could look at another star with the view that we have of the sun, we would be able to determine so much more about the inside of those stars. And we are able to do this for the sun because it's so close, and we can fully resolve those very small variations on the surface.
Cool. I think this, relates from Skylar Thompson. Is it possible to distinguish vibrations from different layers of a star?
Yeah, it is. Actually, I think I have a paper sitting around I'm supposed to read that is something to do with that. Yeah, different pulsations probe different regions, and then there are also different types of variations. There are, so I talked a little bit about what causes of variations. There's got to be something that drives them in some certain way. There's waves that are sort of like sound waves that are pressure variations. We call those P modes, after pressure modes. There's also a type of pulsation called G modes. Those are gravity modes. And those are a little bit more like waves that you might see on the top of the water, propagating along the surface of the water. Those aren't pressure. That's not caused by pressure. That's caused by gravity. If you have some wave, then it falls back down. And those types of waves typically propagate under different conditions, and so we can observe in some stars both types of variations simultaneously, and they come from very different regions of the star, and that gives us additional leverage. I mean, if you see both types of variations, then you can potentially understand the structure of that star in much greater detail.
All the different waves. So another question from YouTube from Sam. After noticing the fluctuations in a light curve, what do you do to differentiate between those that are due to the star oscillations from those due to other reasons like transits, star spot rotation, all the other nonsense that happens? My addendum there.
Your addendum. Okay, well, I'll go with that addendum. We can kind of pick them out directly from these images like I was showing here with solar-like oscillators. This is one type of variable. There's this, you can really see in more detail here. There are these many peaks in the same range of frequency, and they usually have this sort of bell shape of amplitudes on them. And then there's usually also this sort of uptick of this line up to low frequency caused by the granulation directly. Those things always come hand in hand for solar-like oscillators. So you can look at this and right away kind of say, I can say that's a solar-like oscillator. The reason we're doing, this data that I've been showing you, we've been putting into some machine learning algorithms to try to do some of that identification automatically. I can look at these and say what they are. Then a machine should be able to do it too if it knows how. Here, this looks incredibly different. I know that this is pulsating in a completely different way, and I know how to interpret that. The same here, many different signals in a certain frequency range. We also have other information about all of these stars, like how hot they are, how big they are, where on the sky they are, all sorts of things that we can use to decipher this stuff. But there are other types of variables I didn't get to talk about here, like eclipsing binaries. I guess I showed a little animation of what that could look like. But these can look very dramatic. An eclipsing binary that has where two stars are orbiting each other and one passes in front of the other and blocks out some of its light. You get this pattern of very deep dips and then shallow dips and deep dips. And even these humps here that are from the distortion that occurs between these two stars because of the tides that they experience, just like ocean tides on Earth. This looks different. It has this sequence of peaks that are all spaced apart evenly like this, that's going to tell us it's an eclipsing binary. And then Meredith also mentioned rotating stars with star spots is another type of variable. It's not a pulsating variable like the vibrating ones I talked about, but this is where you have something like a star spot, like a sunspot on a star, and that causes the star, when you look at it from this side, to be a little bit darker. But stars all rotate, and so as these stars rotate, we see that dark spot, move across the hemisphere that we're looking at and make the star look temporarily darker. And then when it's on the backside where we don't see it, the star looks brighter, and that creates these brightness variations. Lost my mouse. Oh, I froze PowerPoint. Those create the brightness variations like you saw in that previous plot. So all of these, they look different in the recordings. They look different in the frequency representation, and we can usually pick these out very clearly. And yeah, that's the first step of analyzing these types of data, is sorting through, figuring out what you're interested in, finding the stars that show what you want to study, and then studying those.
Cool. We have, oh, yep. Yes, he did. Meredith?
Sure, fair enough. Yeah, Keaton's been jumping ahead and answering questions other people are coming up with, which is great. There was one final question from YouTube, though, that we can ask, and it's a little more general. The question is from Phil. It's, what sorts of data or what aspirations do you have for this research? Then I guess I would just kind of add my own take on that. Like, what, TESS is great, but like, what's the next thing, or what's TESS going to do next that's going to be even better?
Well, the next thing is, I guess, Plato, which I honestly don't know a whole lot about. But Plato is the next mission that's coming out that's going to do acquire similar types of data. TESS is observing now in an extended mission that it's acquiring more rapid sampling of the brightness of stars. It's recording faster video in a sense. So there's more and better data coming out. But what I'm working on right now, for the most part, with TESS data, is I'm really interested in combining the TESS data with data from another ongoing survey called Gaia. So what Gaia is doing is Gaia orbits the sun. It's another spacecraft. It orbits the sun, and as it views different patches of the sky from different angles, it looks at stars from different positions in its orbit. The positions of those stars appear to shift a little bit because of how close they are. So you can all do this kind of experiment if you'd like, where you hold a finger up in front of something that you can see. You close an eye, hold a finger up in front of something so it covers it up, and then switch which eye you're looking through. Thank you, Meredith, for playing along. If you change which eye you're looking through, then your finger will kind of appear to move back and forth a little bit compared to what you were covering up. And if you move your finger further away and do the same thing, your finger will appear to move back and forth not quite as much. And so when we have this spacecraft that's orbiting around the sun, and it's measuring the positions of stars from different positions, it sees how much they wiggle back and forth as it looks from different angles. And the ones that move a lot are the ones really close, and the ones that move a little bit are the ones really far away. So this is telling us something about how far away the stars are. And when we also look at how bright they are, it tells us how big they are. And I think Gaia has just in the last couple of years provided the best set of measurements of how far away stars are in our galaxy for an incredible number of stars. And I'm really interested in how we can combine vibrational information about the stars with their distance information in one coherent statistical analysis that gives us a very reliable accurate stellar parameters that we can take to the bank, that we can trust, and you know, some of these I think could be real benchmark stars for how well we understand them with such high quality data that we're getting today.
Sorry, had to unmute. So I want to thank Keaton. I want to thank you again for your wonderful talk. I think we're out of questions, and so this is the perfect time to wrap up. So I'm going to clap once again for everyone. This round of applause here. Getting some virtual applause as well. And so thank you everyone for joining us, whether you joined us here on Zoom or on the YouTube channel. Just a reminder that we'll be going live at 8 p.m. Pacific time with Dr. Keaton Bell on Instagram at AOT Seattle, our Instagram page, and we'll be having an interview, and it'll be super great. Bring whatever's left of your beer, and we'll see you in about 20 minutes. Thank you so much.
Thanks, folks.